So first of all, thank you so much for this great opportunity to speak at the One Word PD seminar. It's a great honor indeed. And the great thing is that now the time is quite late in Seoul. So if I say anything stupid, I can just blame the time. So today I want to talk about some work that I did with Jee Jeong Choi. He's at UNIST Korea about proving some instabilities for vortex ring dynamics. So let's begin. So the basic question that many people, including myself, have studied quite seriously is the phenomenon of small-scale creation in fluid dynamics. So small-scale creation is really the characteristic feature in fluid dynamics. So small-scale creation roughly means that the fluid somehow has the ability to create very small vortices, eddies of very small sizes. So the basic question, the broad question is to how to prove rigorously such a behavior purely based on the partial differential equation. So today I will give a brief review of some recent works in this direction and my works on small-scale creation from vortex rings. So the main message that I want to give in this talk is that somewhat interestingly, small-scale creation, or in other words, instabilities in fluid dynamics, can be proved using some variational principles. So that's the message I want to give. And let me start slowly.
Tu n'entends pas. Très bien.
So I want to start slowly with two-dimensional fluid dynamics, which is much simpler. So in 2D, I want to consider incompressible Euler equations in vorticity form. It simply means that I write the evolution equation in terms of the vorticity. So it's omega, which is scalar valued in the case of 2D fluid. So this scalar vorticity function is being transported by the velocity, as this equation says. And the velocity at each moment of time is generated by the vorticity in terms of this functional relation. So the big conjecture, which is wide open, is that for generic initial data, whatever it means, the solution to these two-dimensional incompressible Euler equations satisfy this infinite gradient growth in infinite time. Okay, so in the case of 2D, it is well known that the solution exists and smooth for all finite times. But of course, the norms can become infinite at infinite time. The conjecture is that it becomes indeed infinite unless you really make a special choice of initial data. And this conjecture is kind of clear from various experiments and numerical simulations, but as it turns out, this kind of infinite norm growth, which is a mathematical quantification of small-scale creation in fluids, is very difficult to prove, even if you carefully design the initial data. So one can check out this very nice recent review paper of Dribas and Ilgindi, in which they essentially collect a lot of mathematical results on the long-time dynamics in two-dimensional fluids. So this is the big conjecture, but let me just review some recent works which succeeded in finding some special initial data for which they can prove this infinite gradient growth. Okay. And this is done by hyperbolic flow. So there have been many results in the past, but I want to focus on two important works, one by Denisov and the other by Kiselev-Sver. And I'm sorry for not giving a comprehensive literature here, but you can look at the recent review papers of Kiselev and Dribas-Ilgindi. So at least for certain initial data, they were able to prove in 2D infinite gradient growth. So the basic idea is to use hyperbolic flow, and how this can give gradient growth can be seen from the equation for the gradient of omega. So what I did is just take the gradient part of the vorticity equation, and then you have this right-hand side, and gradient mu is a 2x2 matrix, and hyperbolic point means a point in which this matrix is hyperbolic. So after a change of coordinates, if necessary, this matrix can be like this, with lambda positive. Okay. So if we can arrange the vorticity in a way that its gradient part aligns with the positive eigenvalue of gradient of u, then we get the growth. So the point is how to sustain this hyperbolicity of gradient of u in time. So the big paradigm here is the stability of the instability. And you can look at this nice review paper of Kiselev. So what it's saying is that if you want to prove a very strong instability result, paradoxically, you need to have much more strong stability to begin with. So more strong stability you have, more drastic instability you can prove. And in this paradigm, eventually, Ilgindi and Chen Ho were able to prove finite time singularity formation, and it will be subject of the next talk. But I want to emphasize that even finite time singularity is based on this paradigm. So here, in 2D situation is much simpler. We want to take some nonlinearly stable vortex states and consider initial data which are sufficiently close to nonlinearly stable states. But the requirement is that we want the nonlinearly stable states to have a hyperbolic fixed point. So fixed point in space at which the gradient of the velocity is a hyperbolic matrix. Okay. So here, omega bar, the requirements are, first, it's nonlinearly stable as a steady state of 2D Euler, and it has a hyperbolic fixed point. So the choices of Denisov and Kiselev-Sver in 2D torus are completely explicit. So the choice of Denisov was to take sine of x times sine of y in 2D, and Kiselev-Sverag was to replace sine by the signum function. So in this steady state, the origin is a fixed point and the velocity is explicitly hyperbolic at the origin. And I will show you a picture very soon. But why are these stable steady states? So one can understand stability in several ways, but probably the simplest way is to observe that these states are actually the strict maximizers of kinetic energy. The kinetic energy is basically the homogeneous H-1 norm of the vorticity. So each of these are strict maximizers of kinetic energy, but with respect to different constraints. So I think this one is the maximizer with respect to L2 constraint, and the other one is up to L infinity constraint. But if vorticity is a strict maximizer of kinetic energy, then it is a nonlinearly stable steady state. Okay. But then how to upgrade stability by instability? So this is just a plot of the stream function. The stream function psi, by definition, is the Laplacian inverse of the vorticity. And for those two steady states, the contour plot of the stream function is essentially equivalent. So here these curves are simply the level sets of the stream function, and level sets are nothing but the trajectories in the steady solution of fluid. So I think the convention here is that here the fluid is rotating counterclockwise and is clockwise in these two. So the point is that the origin is a fixed point, and there is a strong contraction along the y-axis and expansion along the x. Okay. And then what you do is you simply perturb the steady state by, for instance, placing some bump function supported at the origin, supported near the origin. Then assuming that the bump is simply being transported by the background steady flow, what it will do is simply expanding in x and contracting in y. So this is what happens to the bump, assuming that the bump not really change the background much. So this gives gradient growth in the y direction. So I hope the picture is clear. Okay, but then I have been considering this problem for some time. So the previous argument was done in 2D torus, and similar gradient growth could be proved in bounded domains as well. But what about if you ask for infinite gradient growth in an unbounded domain, for instance, in R2? So here the main difference in unbounded domain is that in infinite time, the vorticity could simply disperse to all of R2 slowly in time. And then even if you have a fixed hyperbolic point, the strength of hyperbolicity, which is simply the value of the eigenvalue, could decrease with time. And then it becomes unclear if the gradient could become infinite in infinite time. So this is the main difficulty. But a few years ago, I went to a conference and I was fortunate to attend a talk by Krasny, in which he presented a very recent numerical simulations for perturbations near the lambda. The lambda dipole I will explain in a little bit more shortly, but this is just some explicit traveling wave solution to 2D oil. And basically, this is what a lambda dipole looks like. And it has been known for several decades that essentially any perturbation of the lambda dipole filaments in time. The filamentation simply means a formation of long tail, which you see in this simulation. Okay. So while the lambda dipole itself is a perfect traveling wave, if you make a perturbation out of it, the perturbation will start to grow and it forms a long tail. So this is basically the candidate for infinite gradient growth in the whole of R2. So as I told you earlier, essential ingredient in the proof of instability is to first have stability. And what is really interesting is that nonlinear stability of the lambda dipole was proved last year by Abe and Choi, and I will explain this in a moment. So based on this numerical simulations and nonlinear stability, we figured out that this filamentation could be actually proved. So this is the theorem, but precise statement here is not so important. So what is proven here is that if you make some outerward perturbation of the lambda dipole, which can be arbitrarily small and localized, the solution in R2 exhibits infinite time gradient growth, and the lower bound we have is a linear growth, which was kind of known based on numerical simulation. And what is kind of nice here is that we get infinite growth of all LP norms of the gradient for any t between 1 and infinity. So here is a picture of the lambda dipole, which I took from Wikipedia. So this, there is an explicit formula for the solution, but the reason I'm not writing it down is because it's based on the Bessel function or something like. Anyways, this is a traveling wave solution, and in the frame, in the moving frame, it becomes a steady solution, and then you see that these 2 points are hyperbolic. So these are really playing the role of hyperbolic fixed points in the case of R2, although you need to look at in the moving frame. So what happens essentially is that based on nonlinear stability, if you put some bump near the edge, this bump will expand in the x direction and contract in the y. And this is really the mechanism for filamentation. So I will give a little bit of details of the proof because it will appear also later again. So first of all, not surprisingly, the nonlinear stability was proved by variational principles. Essentially what you do, so this was done recently by Abe and Choi, you want to maximize the kinetic energy. So their main theorem, which gives stability, is that in some constraint maximization of kinetic energy, I think you need to subtract some multiple of L2 norm. But they proved that, so this is lambda dipole. Lambda dipole is the unique maximizer up to a shift. And of course, a shift is necessary because all the shifts of the lambda dipole have the same energy. And then based on the variational principle, you readily deduce this nonlinear stability, for example, in L2 of the vorticity. So the formal statement is that for any epsilon, there exists delta, so that if your initial data in terms of vorticity is L2 close to lambda dipole, then for all time, the solution corresponding to the initial data is epsilon close to some shift of the lambda dipole. So here the message is that dispersion for perturbation of the lambda dipole is prohibited for all times, simply because perturbation of a lambda dipole means that it is almost an energy maximizer, and energy is maximized when the vorticity of same sign are close with each other. So the idea is kind of clear. So the initial data, if it's close to the lambda dipole is energy maximizing under some constraint. And energy can be maximized only if the vorticity of same sign are close with each other as much as possible. So that's the idea. And of course, here the problem is that in principle, we do not know what is the value of this shift, because this nonlinear stability is just coming from So the new ingredient, which is kind of simple, is a principle that we figured out, which says that if the vorticity have a similar shape, then it should have a similar speed. So the lambda dipole has a well-defined traveling speed, some absolute constant. And what it says is that if a vorticity looks similar to lambda dipole, then it is almost a traveling wave with similar speed, which means that tau of t is simply the speed of lambda dipole times t, almost. So this is what I mean by speed. The motion of center of the vorticity in x1, so x1 is x. And explicit computation shows that the time derivative is equal to this integral of u1 times omega. And it turns out that this is a positive quadratic form. So this is essentially something like omega to h dot minus 1/2. Not exactly, but it's something like this. Therefore, if we have the control of vorticity in L2 and h dot minus 1, you control the traveling speed. So similar shape means similar speed. And as a consequence, we have that this shift function, which was unknown a priori, must be almost equal to the traveling speed of lambda dipole times t. So perturbation really moves like it's the lambda dipole, and a separate computation can be done to show that the outer part of the perturbation is strictly slower. And this is just another computation. And once the tail separates sufficiently far from the bulk, then it's only becoming slower and slower. So this kind of argument can be proved using a bootstrapping. So this was the ideas. And now I want to move 3 dimensions. And the same question one can ask is, so how to prove small scale creation, or in other words, growth of the gradient in 3D. And here's the 3D vorticity equation. Now the vorticity is a vector valued function. It's a 3D vector. But again, the vorticity is being transported by the velocity, which is generated by vorticity itself at each moment of time. But as is well known, the main difference from 2D is this extra term on the right-hand side, which is the multiplication of vorticity with gradient of the velocity. So if there is some alignment between these two vectors, then the vorticity can grow in ad infinity, unlike the 2-dimensional case. In 2-dimensional case, the vorticity is simply being transported, so the maximum of vorticity is always constant in time. And this quantity, whether it becomes infinite in finite time or not, is a criterion for blow-up versus infinity solutions. And indeed, a recent celebrated works by Elgindy and also by Chen and Ho, they were able to rigorously prove that there is finite time singularity formation in 3D. So in their works, the vorticity indeed becomes infinite in ad infinity in finite time. But what I want to talk about here is the question of whether we can prove infinite time, infinite vortex stretching for 3D solutions, for which we already know that the solution is global in time. So this is the question. So in 2D, there have been many results proving infinite gradient growth in infinite time. But in 3D, we want to ask more. We want to show not only that gradient becomes infinite, but also vorticity itself becomes infinite. So basically, the candidate is to consider the simplest 3-dimensional flow one can imagine, which is axisymmetric and no swirl flows. So here's what it means. So first of all, axisymmetric means that the vorticity and the velocity in cylindrical coordinates are functions of r and z only. So this is what axisymmetric means. The dependent variables are functions of r and z. And no swirl means that the vorticity only has e theta component, and the velocity only has er and ez components. So this is definition of symmetric and no swirl. And it is really the simplest 3-dimensional flow in the sense that if the initial data is smooth, it's not difficult to prove that the smooth solution exists for all time in this case. So there's no singularity under axisymmetric and no swirl assumption. And the vorticity equation becomes a scalar equation in terms of the variable omega theta. the equation is now much simpler. But interesting fact is that still the vortex stretching term is alive, and this term can make omega zeta to become very large. But again, there's no singularity formation for smooth initial data in this case. So for vorticity to become infinite, it must be infinite time. So the question we ask ourselves is whether such infinite growth is really possible. So usually, people write this axisymmetric and no-swirl equation using this new variable, omega zeta over r. Okay. Then the equation is really just a transport equation, as in the two-dimensional case. But it's important to notice that if we write the equation in terms of the vorticity, there is this right-hand side, which can make the vorticity very large. And I'm going to show you an instance where it actually becomes infinite in infinite time. Okay, but before we proceed, one can ask whether you can have infinite gradient growth in infinite time for globally defined growth. And such a result could be proved using filamentation, but now filamentation around so-called Hill's vortex ring. So this is the analog of lambda dipole, but in axisymmetric geometry. But flow lines of this vortex ring is kind of equivalent with those for lambda in RZ plane. And what is nice about his vortex ring is that it has a simple explicit formula. So this is the formula for the Hill's vortex ring. It's R times the indicator function on the unit 4 in the RZ plane. So what I mean by a vortex ring, so vortex ring is not really a precise concept for me, but I just use it to mean some vorticity function, which are kind of localized at a few points in the RZ. So in the case of Hill's vortex ring, in the RZ plane, the vorticity is really localized around some center. And you axisymmetrize it in R3 to get the whole ring. So in this
Sorry, what is domain B?
What is B?
B, domain.
Yes, B. So this is the set where, yeah, R squared plus D squared is less than. It's the unit form.
Thank you.
Okay, thanks for your question. You can interrupt me at any time. So the variational stability of Hill's vortex ring was proved by my colleague Choi very recently. And using a similar strategy as in the case of lambda dipole, we could prove infinite time filamentation near Hill's vortex. So what happens is that you kind of see it from this. So if you just add some tail to Hill's vortex ring, it will just continue to grow linearly in time. And using that linear in time growth, you can prove infinite growth of the Hessian. So this was one thing that we could kind of easily do, similarly in the 2D case. But this does not give the growth of vorticity in at infinity. So how do we get that? So essentially, you can now consider multiple vortex rings. So here's vortex should be considered as a single vortex ring, only one vortex ring in the plane. And if there are multiple vortex rings, there are many interesting interactions, and probably the most simple, non-trivial interaction is so-called leapfrogging. And one can look at this very recent nice paper in which they actually rigorously prove that leapfrogging happens for two vortex rings. But a point is that if all the rings have the same sign, so axisymmetric vortex rings have signs. So the vorticity could rotate either clockwise or counterclockwise. So having the same sign means all the rings are rotating in the same direction. And in this case, there is no mechanism for large vortex stretch, simply because there's a Hamiltonian which is coarse, and I'm not going to tell you what the Hamiltonian is, but the Hamiltonian controls vortex stretching, and therefore the simplest scenario, which could potentially allow for infinite vortex stretching, is when you have two rings, two vortex rings, with opposite signs. And this is what is called the anti-parallel configuration. And of course, then we can make these two rings anti-symmetric, which is preserved by the flow. And such an anti-parallel configuration is beautifully constructed in this YouTube video by Smarter Every Day. I think this has like tens of millions of views, and you can look at it, it's amazing. So what's happening here is that, so in our convention, this could be the Z direction. It can be confusing, but you have to bear this in. And this is the positive R direction. And the rings are moving this way. So the red one moves like this, and the blue one moves. Okay. So this is the geometry of the flow, and its axisymmetry. Okay. So this is to just make the notion precise. By anti-parallel, I will mean that the vorticity is an odd function in Z, and it is non-negative in the upper half space. And this kind of flows was the subject of extensive numerical works. And these pictures are experiments taken from this paper. So basically, you see what happens if you shoot two opposite side vortex rings against each other. And there is a slightly better picture here, which I also took from YouTube. So essentially, simulations show that there are three stages of motion. So initially, so this is the initial stage. If the rings are far apart, then the interaction is very weak, and they move as if they are on its own. So they move like Pierce vortex, for instance. But once they become sufficiently close, they squeeze each other, and apparently vortex stretching happens. You see that the direction in the R direction, so this could be confusing, but again, this is positive Z direction, and this is the R direction. You see that compared to the first picture, the rings have moved outwards to the R direction. And this implies vortex stretch. And once the rings become too thin, it breaks up into many vortex rings, which is impossible for Euler flows, but in reality, there is some small viscosity. And what is important is that the first two steps are essentially inviscid phenomena. So until the vortex ring really breaks down, which is again impossible by Euler's law. And this really suggests infinite vortex stretching should be possible for Euler in this geometry. And I'm just recalling the Cauchy formula just to make sure. So the vorticity, if you compute it along the flow map, it is initial vorticity times phi r divided by r. So it means that if the particles go out in the r direction, it means that vorticity have been amplified by that amount. And this comes from the conservation of circulation, or if you like. And then the natural mathematical question is, what is the rate of this vortex stretching with time? So here, we do not have a stability result, but instead we rely on monotonicity formulas. So let me just speed up a little bit. So this is the main monotonicity formulas. Assuming antiparallel configuration, we define these two quantities, P and Z. So before I explain this, one can record this conservation of circulation. So this is what I mean by circulation. And I'm putting minus of omega because I'm assuming that omega is negative, so that this is actually positive. And all these things are positive functions on the upper half. So since the conservation, circulation is conserved, P is essentially the average of R squared on the support of vorticity. P, you should think of it as the average of R squared on the support of vorticity. And similarly, this quantity Z is the average of Z. And it turns out that these two quantities are monotone in time. So P increases and Z decreases. So I will omit how this can be proved, but this monotonicity was clear from the simulation. So this is again Z and R, and the rings, antiparallel rings, are moving in this way, which means that the average of R is increasing and Z is decreasing. Okay. So this was kind of expected. And now I'm going to show that this monotonicity formulas can give us many instability results. So essentially, this plays the role of stability. So first of all, we can prove infinite growth of gradients and also infinite growth of C alpha norms for any R. But this cannot really give growth of at infinity. But let me just sketch the idea very quickly. So here is the celebrated lemma done by Kiselev-Sfera. And this is just a version for axisymmetric flows, which also played an important role in singularity formation result of Elgindi. So essentially, what you have is that the velocity is this polynomial times some integral I of the vorticity. So I is some integral of the vorticity. I'm not going to explain. And in the case of R3, the problem is that the vorticity could just go to infinity. And this is what's actually happening, as we have shown, as you have seen. And then it simply means that I goes to 0. So hyperbolicity decreases in time. So this is the main problem. But how to overcome this is, first of all, the mass cannot escape to the z direction. The z direction in average is not allowed because we have the monotonicity in z. And it can escape in the r direction, but escaping in r direction is vortex stretch, which is good for us. So in the end, you can deduce norm growth by a contradiction argument. Okay. So the mass either escapes or not. If it does not escape, we get infinite growth by P lemma. If it escapes, we get growth by vortex stretch.
Sorry, what is absolute value of x? What is x? What is x?
Yes, so x is here just yes.
Thank you.
Yeah, thanks for the question. And the second main result, which can be proved using the monotonicity, is a universal growth rate for this quantity. So it turns out that no matter what the initial data is, we always have this lower bound in time. So P of E, again, this is the average of R squared. It must grow at least T to some fractional power. And in particular, it means that in anti-parallel geometry, the support diameter of vortex rings goes to infinity, at least with this rate. So let me just quickly explain how this can be proved. So what I want to really emphasize here is that the proof has a strong variational flavor. Namely, you are really solving the question of what is the slowest possible speed in R under natural constants. And the slowest possible motion in R will give the lower bound. And the precise formulation is as follows. So P is the quantity that we want to show growth in time. So we need to get a lower bound in time derivative of P. Okay. So this is really the question of what is the slowest moving guy? And here's our answer. So E is the kinetic energy, and X is some quantity which is only consisting of conserved and monotone quantities. So that's the point. This we treat as a constant, and somehow the kinetic energy has this relation with P and time derivative of P. And once you derive this inequality, you can get the growth rate in P. Okay. So let me just kind of wrap up here. So we get some growth for this quantity P, and that growth for P can be upgraded to LP growth for the vortice, including P equal to infinity. And the growth rate is unfortunately kind of slow, but at least it becomes infinite with some rate. Anyways, I want to summarize and give some discussion. So this question, I think, is open. So what is the really the maximal rate of vortex stretching in this anti-parallel flow? So I want to mention, first of all, this nice upper bound by Childress, which he first proved T squared and then T 4/3. in time, you see that our lower bound was something like T1/15. Maybe it was 2. So there's a large gap between this upper bound and lower bound. And Feng and Sverak had a proof of upper bound of T². And more recently, Childress, Gilbert, and Valiant, they provide convincing numerical simulation which states that this bound is actually achieved. And this is basically the picture. And I think it will be quite challenging to actually prove this lower bound. Okay, sorry for going over time.